At this point, we've already seen a lot about writing code in C++. We've seen how to create variables, assign values, perform computations, get input, produce output, and create conditional statements. And we've seen several programs. And I hope you've run several of these programs and tried writing a few yourself. But there's more to making a program than just writing code, though obviously code writing is really important. But there are other considerations, like design and testing, that are just as important. So in this lecture, we're going to begin taking a deeper look at what it takes to make a program, and what it takes to make a program in C++ in particular. I want to start out by talking a bit more about the structure of a C++ program. We've been seeing and writing programs already, and to start out with, we'll go back to our very first program, the Hello World program. Let's take a little bit more of a look at a few of the lines that we've glossed over to this point. We've talked before about comments and their usefulness. It's often helpful to start a program with some sort of comment, what we might call a header comment, that gives some information about the purpose of the program. The next line we have is a #include line. The pound sign, which due to social media is now often called a hashtag symbol, has a special meaning. The pound sign is used to designate special commands that are given to the compiler, the thing that's going to translate our program into machine instructions. When a compiler looks at a program that it needs to process, it first identifies any lines that have the pound symbol, and these lines are processed first as special instructions to the compiler. We call these preprocessor commands, since they take place before processing the rest of the code. #include is by far the most commonly used, but there are a few other preprocessor commands, all starting with the pound symbol. The #include statements can bring in new lines of code. Then there are #define statements, which can modify code. And there are #ifdef statements, short for if defined, which can choose lines of code. The #include is a way of saying, there's another file out there that contains some additional functions. Bring that file into this program. This gives us access to any functions in that other file. For example, #including IOStream gets us access to important input and output functionality, like cin and cout. In short, the #includes that we usually begin our program with are importing files to give us additional functionality. Now those files are usually from the C++ standard libraries, which are installed with C++, and so they're available whenever you need them. The next line we encounter is the using namespace command. A namespace is a way of grouping various functions together. By saying using namespace, we're indicating which group of functions we're using. In this case, that's the std namespace. std is a shorthand way of saying standard. It refers to the standard namespace. So, when we read std anywhere, it's common to pronounce it as standard. First, let's see what would happen if we took that line out of our program. When we try to compile the program, we'd get an error, saying something like cout is not declared. Well, that's weird. Didn't we just #include IOStream so that we'd get cout? Well, it turns out that many of the commands, even very common ones, are defined in the namespace. We'll learn more about namespaces in lecture 15, but for now, the way to think of them is as a special name that needs to be added on to the beginning of commands. Here's how the code would look if we had to include the namespaces directly when using each command. Notice how we had to write std::: in front of cout and endl. This is our way of specifying that those are defined in the standard namespace. Now, there are big projects that might require this way of working. There might even be multiple namespaces, since different groups on a project often create new namespaces to clearly distinguish their code. But as you can imagine, it can be a pain to keep writing standard : before each command for a small project where the scope of our using namespace standard is clear. And so, the line using namespace standard lets us say, unless we specify otherwise, we're using the standard namespace. Oh, and this is a C++ command, not a command to the preprocessor, so it ends with a semicolon. In short, this is a line that saves typing, and it makes the rest of your code easier to read. The next line we've been seeing is the int main parentheses line. Now, what this is doing is creating something called a function, which is a set of commands that get executed together. The parentheses show that it's a function. Int means that it returns an integer, and main is a predefined name. When we make other functions later in the course, they'll look a lot like this main function, and our program can have lots of functions defined. But main is a special function. It's the one that the compiler will recognize as the function to start with. The commands that come in the curly braces after main are the ones that will be executed first when the code is run. You'll notice that main starts out with the term int. The way you can think of this is that the main program that results will have an integer value when it runs. This integer value actually has a meaning. If the program completes without an error, its value is 0. If there is an error encountered, it has some non-zero value. The particular value can vary based on the particular error. Sometimes when a program crashes, you'll see a line that talks about exit code and gives a number. Well, that number is the integer value that the main program has, and for an experienced programmer, it can give more information about the type of error encountered. So, those are the key parts at the beginning of the program. We have #include statements so that the preprocessor obtains access to libraries. We have the using namespace standard line to keep from having to state namespaces explicitly. And we have int main to designate where the program starts. I now want to make a point about style. C++ gives us a lot of flexibility in terms of style. Now, unlike some other languages, C++ basically lets you space your code and indent however you feel like. Sometimes different people have different styles of formatting code. The style to use is based mainly on personal preference, unless you're part of a bigger project where coders will try to match each other's styles for consistency. Now, we've talked about flexibility and spacing before, but I want to illustrate a couple of examples. First, here's the same Hello World program we've been seeing. The only difference is that I moved the opening curly brace of main up onto the previous line. I kind of prefer this style of coding, where the opening brace is on the same line as the thing it belongs to. But other people prefer the earlier method, where the opening brace is on its own separate line. In this course, I'll switch back and forth a bit. It makes no difference in how the code works, so you should get used to seeing different ways of writing. I'll point out one other thing. We have a blank line in the program, in between the using namespace standard line and the int main line. Blank lines, or white space like that, can help to separate parts of the program that are conceptually different. If you find that you're dealing with a pretty different concept than the code above it, you might want to add a blank line. Conversely, it's possible, but not usually advisable, to make code really compact. For example, we could put basically the whole program on one line, like you see here. We can remove most of the spaces, remove the new lines and indentation, etc. Now, to the compiler, this code is no different than the code that we had just before. However, it's a lot tougher for a person to read. Notice that #include must remain on a single line by itself. Remember, that's not actually a line of C++ code, it's a preprocessor directive. #includes and other lines starting with pound will take up exactly one line each. But except for lines starting with pound, it's possible to break up any other line, and almost anywhere within each line. This is still the Hello World program, but there are new spaces and removed spaces, weird indentation, etc. The only constraint was we couldn't break up the phrase Hello World that was in quotation marks. This was actual text that had to be kept as it was for the output to remain the same. But basically everywhere else was open for changing. Now obviously, this is not a good way to write a program unless your goal is to confuse the person reading your code. And believe it or not, there's actually a contest held annually, the International Obfuscated C Code Contest, where the whole goal is to create C code that's as difficult to understand as possible. And there are some really creative ways that people manage to obfuscate their code, from picking strange variable names to creative use of spacing, sometimes so that the code looks like a picture. It's all done for fun, to show in an ironic way the flexibility of writing in C and the importance of good programming style. As we develop our programs, we want to do so with a style that as much as possible makes it clear what the intention of our code is. And that can involve picking good variable names, using good spacing and indentation, and organizing the code in a logical manner. So, how do we make sure our code is organized logically? This is where design comes in. I'm going to describe one way of design that's a good starting point for initial programmers. But I'd be remiss if I didn't let you know that there are other ways that people design and develop software, doing things in different orders, involving teams of programmers in different ways, and so on. To begin, let's step back and think about the big picture. Usually, our program begins with some idea, the thing that we want to be able to do. Now, often this is just a vague idea at the beginning. And from there, we try to get more specific. We need to determine exactly what it is we're doing, what we expect as input to the program, what computations we want to perform, and what we want to be able to output. And these are often called the program requirements. At this point, we have two things that we should do. The first is to determine test cases, and the other is to design the program itself. Following program design, we'll code up our program. And as we code, we'll use the tests that we determine to continually check that our code is on track. When we've written all the code and passed all the tests, we'll have achieved success, a working program. Now let's look at the details of this programming process. First, let's talk about tests. In many ways, being able to pass tests is the most critical ability of a program. This is why some people believe that coming up with tests should be the very first thing you do when developing a program. This approach is called test-driven development. If you've developed a sufficient set of tests, then having a program that can pass them means that the program works correctly. The only way something would be considered an error or bug is if it caused a test not to pass. Anytime you hear of a software failure, you can think of that as something that wasn't caught in testing. The software developers didn't think to test some particular case, and so an error got left in a program, leading to a problem. Because of the impact that errors can have, testing is often a major part of a software development project. On professional projects, the estimates vary from about a quarter to about half the total time on a project being spent in testing. But more important than knowing how much time to spend is knowing what to test. Here are some good rules of thumb. First, think of the boundary cases, also called edge cases or corner cases. Imagine that you're on a chessboard. In a typical square, you'd have 8 neighboring squares, 1 on each side and 4 on the diagonals. But the edges and the corners of the board are different. There are neighbors missing. If you always assume you have 8 neighbors, you'll run into problems at edges or corners. Often, problems in programs come from forgetting to handle edge cases correctly in the code, so testing edge cases is a good place to start. In many programs, the edge cases are wherever there's a break or boundary of some sort. So, let's say that we had a test where we wanted to give a discount to people under 18 years of age. Well then 18 would be an edge case, and so would 17. Those two ages would be right on the boundary, and would be some of the most likely places that an incorrect computation might occur. After you've thought of the edge cases, then try to think of special cases and invalid options that users might enter. If you're writing a program that handles people's names, you might assume that everyone has a first, middle, and last name, each made up of letters with an initial capital and the rest lowercase. And in the US, that accounts for a big majority of people. But you probably want to ensure that you can handle cases where someone has an apostrophe or a hyphen in their name. Or you might want to make sure you handle cases with different capitalization. Or handle people who have more or fewer than 3 names. Now, like with edge cases, the idea is to think about what assumptions you might have made for the typical case and ensure that you handle the other cases that might come up also. And finally, you want to test some of the regular cases. Usually just a couple of these are fine. If you handle the edge cases and the special cases and a few of the more generic cases correctly, that's usually sufficient for testing. Let's do a quick practice. Say you're wanting to write a program that handles dates. What are some of the days of the year that you might want to include in your test cases? Well, first, think about edge cases. For dates, this would include the first and last day of the year. You'd want to make sure you could handle January 1st and December 31st. You'd probably also want to check that you could handle the first and last days of some other months correctly, including 28-day, 30-day, and 31-day months. And what about any special cases? Yeah, we have one, February 29th. You'd want to make sure that you handle February 29th and leap years correctly. And finally, you'd want to test a few random dates spread throughout the year. Overall, if your program worked for all these cases, it probably works everywhere. Again, it's a good idea to think early about your tests. Sometimes thinking about the tests will help you remember things you need to include in the software design itself. When you've thought of your tests, it's a good idea to write them down. Often this is as simple as writing down an input and what the output ought to be. Once the tests have been considered, it's time to start thinking about how we can actually develop our program itself. The usual way we begin to approach this problem is with something called pseudocode. Instead of writing actual code right away, first we write out steps in more general terms that describe what we want the program to do, but that aren't actual code themselves. We can write those steps of pseudocode as a series of comments, and then we can translate that pseudocode to actual code. Let's walk through a sample program. Suppose that we go to the doctor one day and have our blood pressure taken. We know the blood pressure number, but don't necessarily know where that falls in terms of healthy or not, and we think we'd like a program to help with that. Now, let me caution here that I'm not a medical doctor and I'm not giving real health advice here. This is going to be for illustrative purposes. So, what are the steps we'll want the program to follow? We've seen before that many programs follow a basic pattern: getting input, performing computations, and producing output. For input, in this case, we want something simple. We want to have a user type in the blood pressure. As for computation, this should be pretty easy. We'll just use the blood pressure to classify someone's level of hypertension. A real medical professional would probably want to take other factors into account, like age and lifestyle habits, but we don't have that input in this program. And for output, we'll just output to the person what their category is. You could imagine a more complex output, like possible recommendations for lifestyle changes, but again, we'll keep things simple. So at this point, we have a clear idea of what we want our program to do. And it's now more specific than just a blood pressure analyzer. In terms of categorizing blood pressure, we'll use a set of conditions based on looking at the systolic and the diastolic blood pressures. We're going to want to implement these concepts in code. Now, this program is relatively simple, so our actual design process is not too complicated. We'll have a series of steps: getting input, classifying the category, and producing output. Since all we're doing when classifying the category is outputting the result to the screen, we can do that at the same time as we classify the pressure. We can write some short pseudocode to list the various steps we'll need to follow. A good way to start when facing a programming task is to take the pseudocode steps that we know we'll follow and transform them to comments. Then we can go back later and fill in the comments and the code between them. These comments serve two purposes. First, they provide an outline that we can follow when developing code. We'll have the comments there and just need to fill in the code corresponding to each one. And second, they'll serve as documentation for the code later. It will be clear when we look at the code which parts belong to which. So, we first outline our program. We'll put in the standard information we discussed earlier: a comment about what the program is doing at the top, the #include of IO stream, the using namespace standard line, and the declaration of main. Inside of main, we'll enter our comments showing what needs to be done. Those came from the pseudocode steps. We've now got our program design. We can start filling in parts of the program. As we do so, we'll want to frequently stop, compile our code, and make sure it's running as expected. The first part to fill in is the input section, where we want to read in the blood pressure by having the user type it in. We first need a couple of variables to hold the two blood pressure values. We'll name these systolic and diastolic. And since blood pressure numbers are always reported as integers, these will be an integer type. Then we'll ask the user to enter each of these and read them in. We'll have a cout statement that outputs instructions to the user. Notice that there's no end line here, so when users type information, they'll do so at the end of the line of text that was just output. We read in systolic first and diastolic second. So, what's the next thing we should do? If you answered, go on to the next comment and fill it in, that's not quite right. At this point, we've written a full chunk of code, and it's time to test it. We'll create one line of output to make sure we know what we read in, just to ensure that the data was read in correctly. Putting in output statements is one relatively easy way to do a quick check that variables have the right values. So, in this case, we add one cout statement, and we try to compile the code to test it. What happens? Oh, we got an error when we compiled. Now, your compiler might show the error information differently, but it should show something like this if you type the code just like I did. This error says that in the function main, on line 12 and 11 characters in, an error was discovered. 12:11 means line 12, that's the first number, and character 11, that's the second number. It then gives us a hint as to what the error is. In this case, it says that a particular variable was not declared in this scope, meaning that we're trying to use a variable we didn't declare. Now, if you look, you'll see what the problem was. I misspelled diastolic, leaving out the O. Notice that the compiler can only give a hint as to what the error was. It won't tell me that the real problem was a misspelling. It just looked like I was trying to use some variable named diastolic, which didn't exist. Fortunately, that's easy to fix, and if we run the fixed program a couple of times, we'll see that we're getting the right numbers output. We enter a number, and we see the same number output. So, we can remove the output line that we put in for testing, and go on to the next section. We next fill in the portion of code around the next comment. In this case, we're checking for elevated blood pressure. To do this, we have a conditional. We check to see that the systolic is at least 120 and no more than 129, and that diastolic is less than 80. And if this is the case, we'll output that the person has elevated blood pressure. After writing this, what's the next thing to do? That's right, now we test. What would be some good values to test this with? We want to handle edge cases, so systolic pressures of 120, 129, and a little on either side, plus diastolic pressures at 79 and 80 would be worth checking. Plus, we should check some more typical values, so values like 125 over 75, 125 over 85, and 110 over 70 would all be worth checking. Now, for the sake of time here, I'm not going to show all these tests, but I recommend that you take a couple of minutes to check that each of these values comes out correctly. Next, we'll go ahead and fill in another comment area. In this case, the check for and then the response to stage 1 hypertension. The situation is very similar to the earlier case, but with a different condition. It makes sense to use the else-if construction to write this code. So, in the case where the previous condition failed, we now check a new condition, in this case to look for stage 1 hypertension. That occurs when either systolic is in the 130 to 139 range, or the diastolic is in the 80 to 89 range. Our condition will be more complex. When we've written this code, an else-if clause where we use comparisons of systolic and diastolic levels to compare the limits, and a cout statement to print, you have stage 1 hypertension. So now we should test it. What would be some good tests to run? Well, we can test our edge cases for both systolic and diastolic. So we can check 130 over 80 and 130 over 89, along with 139 over 70, and so on. We can also check a few in the middle. Let's try some out. We enter 130 over 80. That is in the stage 1 hypertension area, though at the lowest level of both. Sure enough, our program correctly outputs that information. Now we try 130 over 89. Wait, we didn't get an answer. That's weird, there must be a bug somewhere. Well, if we look at the code, we can see one clear problem. I accidentally wrote diastolic less than or equal to 80 instead of greater than or equal to 80. Whoops. Well, that's an easy fix. We just changed that less than sign to a greater than sign. Let's make that change and test again. Now we get the right answer, so we evidently fixed that bug. Okay, now let's keep testing. Let's try some more average cases, like 135/75. This should be hypertension, but again, we're not getting a line of output. That's an issue. Looking at the code, we can see another problem in our condition. The line with double ampersand means that both systolic and diastolic have to be in a certain range, when the actual result should be an OR. So, we changed double ampersand to double vertical bars to fix that line also. This code now seems fixed, but we should run all of our tests to make sure. Keep in mind that anytime you find and fix a bug, you want to retest everything to make sure that nothing broke. If we keep going, we can fill in the rest of the program, section by section. We add additional else-if sections with more conditionals to check for the various cases. So, in this case, we handled the check for stage 2 hypertension, for being in the danger zone, and for hypotension. And in the best case, when we don't fall into any of the bad categories, we get to print out a message saying that blood pressure is in a healthy range. Now, as we do this, we should continue to test along the way and make sure that everything is working as we expect. In the end, we went through the entire process. We went from an idea to requirements, we developed test cases, and we designed the program. As we actually wrote the code, we ran our test cases and used these to find where the problems in the code were. Now, as we conclude this lecture, I want to make one point that's important to realize, especially as you're starting out. In the example we just ran through, I had several bugs. Now, these were in there for illustration purposes because everyone has bugs in their code. The very best programmers in the world will all have numerous bugs as they write their programs. Now, it's true that as you become a better programmer, you make certain mistakes less frequently, but everyone still makes mistakes. They're a normal part of programming. What's important is being able to find and then fix your mistakes. And that's why testing is so important. It helps you identify when you've made a mistake in the program. So, as you develop programs, don't worry that you encounter bugs and errors. Keep testing frequently as you develop your code, and you'll catch your bugs sooner. The sooner you find a bug exists, the easier it is to find out what caused it and then to fix it. If you wait too long to test your code, you might find that you had a bug early on that's more difficult to locate and more difficult to fix. Learning how to find your mistakes will not only teach you to write cleaner code, it will put you on the path to becoming a better programmer. In the next lecture, we'll look at how we can have the computer do one of the things that computers do best, being repetitive, as we turn to the subject of loops and iterations. It'll be fun. It'll be fun. It'll be fun. See you there.